Gray from UC Austin, and it's on the title.
Good. Well, it's great to be here. I thought that morning session was fascinating. I know there's a lot of good talks coming up this afternoon too. But it's a real transition at this point from looking at the program from areas of understanding coherent excitations in materials, coherent energy transfer, plasmons, manipulation of structures using these ideas in terahertz and so on. And I'm going to talk this afternoon about mostly stochastic incoherent phenomena involving conjugated polymers. And this talk is also relevant to other new sets of quasi-amorphous materials that are, well, not necessarily new, but that are receiving a lot of attention at the moment, such as SIGs, which are the basis of some of the most promising photovoltaics. Basically, the problem goes like this. I think we talked this morning about the fascinating progress being made through all optical methods of generating maybe over some period of time square meters or yards or whatever of nanostructures. Absolutely fascinating. I mean, anyone who's done the calculation knows what a great advance that is. But we're talking about things for which there will be made in the next few years square miles. Okay, this is, when you see what's going online in photovoltaics, and we're talking about, 100 megawatt energy generation per values coming up that are needed for photovoltaics. These are fantastic needs. And these materials all have the following similarity, and that is that they are disordered, they're amorphous, they're nanostructured intrinsically, and they derive their efficiency, they derive their good things and their bad things from the local molecular level and nano level details of the system. If you look at theoretical modeling for energy transfer in photovoltaic systems, let's say energy moving toward an interface or separating at that interface and so on, those theoretical models which are used to analyze the devices that are being today are mostly phenomenological models that to a very large extent assume uniformity throughout the device and throughout the material and replace all that rich nanostructure with a couple of parameters. So a few years ago, my group got very interested in trying to see whether those models worked, and in particular, if there was something about the local structure of conjugated polymer blends and even pure conjugated polymers that suggested the macroscopic models were overly simplistic and that there was a rich inner structure of this energy transfer, and maybe that could be used. John Gray, who did much of the work that I'll present today, although my talk's pretty broad, I think said it beautifully in trying to understand energy transfer and charge transfer across an interface. And the reason charge transfer and energy transfer keeps appearing is in this kind of work is the two main applications of kind of materials I'll talk about today are OLEDs, where electricity makes light, and photovoltaics, where light makes electricity. And in both cases, we have excitations, very weakly excitonic systems or delocalizations over the nanoscale no longer. And these excitations are traveling and in an environment that is very densely populated by polarons from negative and positive charges. And there are different types of excitation, singlet and triplet excitation. They're all interacting, and sometimes when you really begin to realize how nanostructured they are, as we did in the late 1990s, using near-field scanning optical microscopy, we realized that this system is in need of many new experiments and theories to handle the distance scale for energy transfer, the fact that mechanisms for energy transfer probably are spatially dependent in what is now unknown way. to get around this problem, there are a lot of approaches, and some of them even taken by other people in this room, one of which would be to take a near-field scanning optical microscopy tip and try to make it small enough so that you could look at individual domains so you can deal with this. Let the system have its accidental nanostructure, but try to get down to that level and deal with that. And the problem with that approach is practical. And one is that that's a surface technique, and often what you're interested in is bulk. So these devices may be 100 nanometers thick, but you need to get down to 5 nanometers to be able to handle the problem. So it's really an embedded interface inside the device, 20 nanometers in, and how can you do that with a near-field tip? There's another practical problem, which is it's very important that the devices be clean, that there isn't oxygen and water, and that they not be perturbed by the beautiful plasmonic effects of the near-field tip. You can put this all together in principle, but it hasn't yet occurred in a consistent, reliable way so that that works to understand how it all happens. Instead, what we've done is to take a different tack, which is also perturbative, but turns out to, at the moment, seem to work fairly well, and that is to merely cut the device up into little pieces and then build in a parallel sandwich way billions of devices that are far enough apart that we can optically address through a transparent electrode each of them and build a nano OLED or a nano photodiode or a nano photovoltaic system, and then have each of these nano systems be a representative sample of it, and then looking at the distributions you get over this ensemble, single molecule ensemble or single particle ensemble, determine about the NOG, and then we can play a trick with sort of an off-bow principle of devices. We can go from very short chains, which are molecular-like, to larger chains, which begin to build morphology, to aggregates of chains, which now represent some piece of the device, up to as large as you want by chemical techniques, and begin to see the device physics in an amorphous system build by starting off with the elements. And needless to say, I wouldn't present this all this way if it wasn't true that a single molecule doesn't have the same device physics as a bulk material. So one question asked, what do you guess? What's the distance scale for which a material becomes bulk? Now, we know in quantum confinement and all those issues about Bohr radii and characteristic delocalization lengths, but in an organic material, which is a one-dimensional conductor, are there any other characteristic distance scales that appear in this problem that control energy transfer and electron transfer? And we'll talk about that. So this is the basic idea. Happened a few years ago in our group. We shine light. We always detect with emission because it's more sensitive. And this is a device in which a single polymer chain, which is some 20 nanometers in radius, involving several hundred individual localized chromophores, if you will. There's one pure polymer chain, but these phenylene vinylene polymers fold and due to other effects into structures where excitations are coupled but localized. And we're looking at a chain like that as we are adjusting a bias on a device. And when the bias goes above a certain value, then a charge enters the device, and you can look at the interaction with the excitons with the charges too. So it's a little laboratory. The laboratory is a nanoparticulate system that is wired on both sides or one side to an electrode. We're shining light on it, making excitons, and we'll be studying that. Okay. So this is the basic experiment. Yes?
What is the nominal thickness of the device?
The total device is typically about 150 nanometers. The layer where the molecules are in are just about something on the order of 10 nanometers. The molecules reach across a layer, or may just be connected on one side of a layer. That's, in most cases, we use a capacitor structure, so you just have to inject charge or pull it out. It's a little bit easier for managing the fabrication. You don't have to connect on both sides. And these, by the way, are very different from I know many of you are quite aware of molecular electronics, where people put small oligomers between two metal particles, and you get all this wonderful jumping around and understanding these structures. These systems don't jump around. They're very stable. They're made by fabrication techniques for the OLED industry. No oxygen, no water. The real challenge here is making the devices. They're pretty easy to do experiments. And here, I think we saw a moment ago what's going on here. These individual glowing spots there are molecules undergoing ordinary fluorescence, and the bias on the device is being scanned, and you can then study each individual one indirectly.
These are molecules on nanoparticles.
These are, that particular example is a single organic polymer chain, which is isolated in an environment. Yeah.
So it's embedded in an environment.
Right. And we're going to see all sorts of environments. We're going to see dry environments that are completely electrically isolated, so all you're doing, no fields or anything, all the way up to electrochemical cells, where one side of the molecule is immersed in a Helmholtz layer. Right. And so it's very chemical. And what do we get at? We get at the distribution energies of exitons in the system, and its impact on energy transfer. Often in energy transfer theory of one type or another, incoherent, and you need to know, is it a Gaussian distribution of energy gaps? Is it bimodal? And additionally, what is the spatial distribution? It's not enough to know the energy distribution, but how are they distributed in space? And this is the kind of information we can infer, and we do. Also, not just questions of optical excitations, but also polaron energies, which sometimes in this business are called HOMO energies, understanding the local ionization potential and how it, or electron affinity, and how it varies in the device. The interaction dynamically of polarons with excitons and processes, as John is going to talk about, so I won't much, is electrode processes. Now, this is the basic system. I know it's a little bit hard to see, or impossible to see from even the first row, but that's a benzene ring, and then there's a double bond, and another benzene ring, and a double bond, and I feel like everyone in this audience understands this very well. I'll just say it for completeness then, that a chain like this, and I'm just going to draw that straightened out, might go across the street, is what we're dealing with. It has some greasy groups on the side to help it become soluble and fold into a structure. And even in a system like this, if it were perfect, even if it were perfect and were symmetrical, due to electron correlation effects, optical excitations are limited in size in these systems to compact excitons on the order of 10 or 20, the order of 5 to 10 double bonds. Now, however, in a system that's perfect with no disorder at all, that would move at high velocity up and down the chain if you created it. In our systems, they're furthermore folded and so on, so those excitations become localized and primarily move, not by motion along the chain in a coherent way, but by first or resonant energy-like transfer to hop to a nearby site of lower energy. Just very quickly, the conformation of these polymer chains was the first thing we got interested in the late 1990s and early 2000, and this led to a very non-orthodox theory that Peter Roski and Beeman Baji and I put forward about borrowing some ideas from an outside of polymer physics into biology about a particular cylindrical type conformation, which I think is now generally accepted. And because of this effect, what happens on these systems, if you have just a single polymer chain that's not too big, let's say of the order of molecular weight 1,000, is that there exists a Poisson number of low energy sites that have their energy shifted quite off from the main band of states due to some packing interaction in the chain. So let me explain what I mean by that. If you took this chain and cut it into chromophores and put them isolated in a clean environment with no impurities, they'd all have about the same energy. Not high resolution. You know, if you did it with high resolution, they'd have different energy. And energy would slowly transfer between them, very slowly, just stuck because of the having almost the same energy. What you want is to have one of them have lower energy so there's greater overlap. And what happens is the polymer self-assembles. It goes into a conformation that produces, turns out, a Poisson number, because there's a small number of them, of low energy sites. And the energy hops from anywhere in the chain effectively to that low energy site. Now, of course, if you had 20 of them, you would be thinking less about Poisson, but it turns out there's often 0 or 1. So one of the consequences of that is that in the bulk polymer film, the absorption, depending on how you make it, these are spin-coated films, depending on if you don't process this film, the bulk polymer film does not have the same overlap in with the emission of the polymer. The emission is shifted, but 99% of the chromophores in the bulk polymer have this energy and should emit this is the polymer absorption, should emit right here. 99% should emit right there. But they don't emit right there, they emit there because 1% of the polymer chains in the sample immediately, within a few picoseconds, accept all the energy from the 99% of the sample that you absorb into. So there's a Stokes shift because of rapid energy localization, because of a bimodal distribution of exciton energies, and an accidental overlap of the absorption of these weak self-formed traps, trap sites. From that, this is the bulk polymer. This is what's used in all the devices, and this was never really driven home until we did the experiments and showed that if the polymer chains are short enough, so the probability of having one of these acceptor sites is very small. The emission now moves from here to the higher energy in resonance with the absorption, because you've interrupted energy transfer. And there it is. There's the emission that would be there if you could cut off energy transfer. So the Stokes shift is from energy transfer, and the acceptor sites are due to folding of the polymer chains. Now, I do want to point out that that's a very low resolution, crude view of the system. You can look with higher and higher resolution by going to low temperature, making smaller chains, and doing a better job of understanding what the distributions of energies are. If the chains are very small, we don't get this red site phenomena. You don't get the red site phenomena because the red site phenomena that I'm talking about, these sites that accept the energy and are responsible for the emission, appears to be the consequence of the first bit of morphology in the system. This is morphology. In other words, it's not a molecular level phenomenon. It is a larger mesoscopic, or somewhere in between meso and nanoscopic phenomena due to chain packing that has a consequence in the micro.
Quick thing.
Yeah.
You're spin coating these, and it's just a pure polymer.
Right, and not in these experiments. In the single molecule experiments, we're diluting the pure polymer with PMMA to cut off energy transfer and so on, and then using short molecular weight to stop energy transfer.
The question I have then is if it's so why, even when you make the chain short, don't you get any exciton transfer between chains? They're right there.
So when we do it, I'm sorry, that's a really good point. So in the bulk polymer with no added PMMA, a short chain and a long chain is the same spectrum.
Yeah.
Absolutely. In fact, that was, Keith brings up a beautiful point. The long and short molecular weight on a pure film is the same thing. Except if you get it so short that you disturb the quantum delocalization along the chain. But that would be very short. That would be 10 nanometers. And I'll just quickly mention this. This is these individual stick structures here are taking an ensemble of molecules at very low temperature where the spectra are extremely sharp and building up the ensemble in much more detail there. And you really see the intermediate states in energy transfer. And what's really fascinating is fascinated people tremendously about this area is two things. One, that in many cases a single polymer chain involving as many as 30 or 50 chromophores, if you will, sites where the energy would be stable, emit perfectly from the lowest energy site. Okay. Two, that there is this bimodal distribution, which is our sort of claim to fame, resulting from the morphological effect on the exciton energy. Why is there two sites and what is going on there? Yeah, sure.
Can you, in fact, design a copolymer when the conjugation part will be interrupted, the non-conjugated?
Yes, and we did that, and it does nothing to slow energy transfer down.
That's right.
Right, because there is not energy transfer along the backbone of the chain, but energy transfer through space because of this folding of the polymer into these cylindrical conformations. Absolutely, and that was a really critical result. So each of these things, you know, they sound so simple, you know, and they sound like you shouldn't have to do single molecule to get at this stuff. These things should have been available, but it turns out what you're fighting here is complexity. So by moving to the next lower level where you can sort that out, you can ask those questions. It's through space energy transfer, not a long bond. Now, what I did want to show you is that for low molecular weight polymer, you get the red and blue site. For high molecular weight, it doesn't quite show up here, but you tend to get more of the red site. This is a little bit lower because you're allowing this morphology to form. For oligomers, which don't have the ability to fold on themselves, you only get the high energy side. And then you take about 50 polymer chains and assemble them together by a chemical technique, co-precipitation, and look what happens to the energy spread. Okay, so I want to be sure this is a histogram of different molecules or particles, each with their own energy. Now, we all know when you get to a bulk sample, every part of the polymer will have the same spectrum. Because if you average over a piece which is big enough, if you sum over a piece which is big enough, it's going to be the same whether you look here or there or here or there. You've reached the bulk limit. You only get this spreading out of energies when you get small enough that you interrupt an energy transfer. And small enough so you can sample the heterogeneity of the system. And this amazing effect where you move into aggregates and the spectrum both shifts red a little bit and the histogram narrows tremendously is the bulk limit. And the size distance where that occurs is about 15 nanometers. And what there appears to be is a cooperative folding of the system when it gets large enough to really start producing a lot of these red sites. Yes?
Is it feasible to engineer the polymer in a way that you could crystallize it, you could cool it and crystallize it, the chains are no longer folded in themselves, and in that way affect the energy transfer now by disrupting some of the localized time?
Right. So, the question was, can you very much alter the system such that you favor interchain over intrachain? And the answer is that these particular polymers, which have these greasy side groups, are hard to crystallize that way. But when you do crystallize in that way by thermal annealing, you start appearing a whole new set of sites. So what is the key here is, and I know many of you know about this, is that if you take aromatic systems and you bring them too close together, the pi systems interact and you get a phenomenon called self-quenching, where the emission then goes away and the energy shift very red and so on. These polymers were designed by Andy Holmes and other people during that period to have big alkyl groups in the chain to keep the chains away. And what tends to happen when you try to start crystallizing them, you start letting the chains pack so carefully that the polymer chains can get closer together, and then all hell breaks loose. You start seeing red sites which have names, they might as well call them SAM and so on, because no one knows what they are. And when you start looking at the powder diffraction, it's very clear that you're getting local crystals. Right. As a result, well, we do it for the optical bands. It is reasonable to suspect that both the optical bands and the electronic true charge transfer states are getting these little funny bimodal distribution of states due to these local crystallinities, and that they are totally dominating the energy and charge transfer in the system. So it's a very interesting insight into what is right or wrong about these materials, depending on whether you want the energy transfer to be very long range or not. Now, it turns out I've been talking about light excitons, singlet excitons, fluorescence, they're not really very excitonic. But you can also look at the triplets or dark excitons. And the way you do that is you take a single nanoparticle, turn the laser on, and this is some 10,000 cycles, but it's one particle. You turn the laser on, and you see on the microsecond time scale, depending on the light power, the emission go down. And what you're doing is you're changing the time average probability of a dark exciton to be in the chain. And the dark exciton, which is a triplet state, is a very efficient quencher of singlet states. So you're turning the system on, it emits, and then it builds up a triplet, and that makes its emission go down. So you can do triplets, and we did a lot of work on triplets and localization and exciton interactions. Now let's build up, I want to go fast now, build up a device, and this device is a capacitor. We're going to be injecting from a whole transport layer polarons. Each molecule will be a nanocapacitor. We'll put a charge in, or more than one, depending on what we do. And we'll do all that single molecule spectroscopy, and that's to look at singlets quenching by polarons, singlet quenching by triplets, triplet quenching by polarons. One of the effects from doing that, ignore that thing for the moment, I can talk about that later if you're interested. There's more going on in these devices. But when you get the bias sufficiently high, you inject charges, and that makes the emission quench. And if you take the same data that I showed you, but plot the derivative of it with proper versus time, with proper calibrations, what that looks like is a pseudo-electrical current, because the charge is going in and causing quenching. So what you're looking at is a kind of electrical current, in other words, electron charge injection events per second. And if you plot that versus bias, these curves for the chemist will look familiar, I hope. They look just like cyclic voltammograms of a polymer layer. I hope some of my chemist friends recognize that. This is one polymer chain scanning several thousand times, scanning faster and faster. When these curves pull apart, you're now actually beating the kinetics of charging that molecule, and this is measuring electron transfer rates one molecule at a time, and they are distributed. No heterogeneity in the system. Now, one thing about that previous data, and especially the one before that, I hope someone was saying, well wait a minute. Victor was probably saying, well, wait a minute. If this is truly one injection of a charge, how did it go from intensity 1 to intensity 1/2? I could go from 1 to 0, but how did it get to 1/2? Well, that was a time ensemble. That was one molecule, but we averaged it 1,000 cycles to improve the signal to noise. You can do single cycles, turn the laser intensity up, you get a little more intense, and when you do that, as you approach the 50% point with your Fermi potential at the molecule, at the 50% point, the molecule jumps back and forth between 1 and 0 as the charge is thermally jumping on and off. And that's what you see, those little pulses right around 50%. Now, some of you, who know about molecular electronics, I mean the kind that people do with molecules connected to electrodes, will recognize there you measure current. And this signal to noise is many thousand times, or more sensitive than current, because we measure photons and we just keep probing the system as much as you want until it dies to measure the state of the system. Okay. And you can do both at the same time, modulate the light intensity and modulate the electric field or the bias on the electrode. And by doing that, sorting out the quenching of the triplets and the singlets. In other words, the dark excitons and the light excitons. And that's an interesting story for the chemists. Triplets are quenched with tremendously higher efficiency than singlets. But that's because triplets live a long time. The actual rate constant is higher for singlets than triplets. But triplets live so much longer that the efficiency of quenching by charges is almost, 100%. And what that means in an OLED, if you're trying to run an OLED on triplets, beware. Triplets will really be quenched very easily by positive charges in order to bring them down to the ground state by an electron transfer mechanism. I don't think I'm going to talk too much about this. I'm just going to switch for a second to electrochemistry. So the exciting news for us about that previous work is that we could effectively measure the local Fermi potential in a device by distributing molecules in individual places. So far I've been talking about using this as a trick to learn about the molecules. But once you understand the molecules, you can now distribute them, pepper them through a device. And the Nernst equation basically says that if the potential is more oxidative than the HOMO level of that molecule, it'll be positive. And if it's more negative, it'll be neutral. So the molecule is a little separate, little Fermi potential measure As long as you're close to that Fermi potential, you can do that. So we did that and published a couple of papers in Applied Physics Letters of mapping the potential in the device. And one thing we learned from that, is we had suspected before, is in a dry device, an ordinary photovoltaic or OLED device which doesn't have an electrolyte, it's very, very complicated to model the potential in the device. So we can map it out, that's good news. But we wanted to go further in understanding the HOMO and LUMO levels of these polymer chains. And what we did was spend a little time with Al Bard, one of my colleagues in chemistry, perhaps the world's most famous electrochemist. And Al explained to us something that I heard about many years ago in school, and that is that in electrochemistry, because of the electrolyte, because of the potentiostat, you can say exactly what the Fermi potential is at the interface of the electrode. You can dial it in. And now, what it allows us to do for molecules is very precisely measure, even to 1/10 of an eV, the oxidation reduction potential of an individual molecule by sitting it in the Helmholtz leg. So that's what we're going to do here, and we're going to do molecules and also aggregates of molecules, these pseudo-bulk materials that are big enough to be bulk-like. And that'll be the final topic. I wonder, how much time do I have?
About 10 minutes.
10 minutes, okay. So I'll go quickly here. So these are oxidation reduction curves in the device where there is an electrolyte, and using electrochemistry we have these oxidation, determine the quasi-Fermi potential very precisely, and we were able to do that to not only measure the onset for oxidation in the ground state and measure E0 or E1/2, depending on what your HOMO energy, the beginning of the HOMO distribution, but we were also able to do it for the excited state, and the excited state is the one that's produced by a photon, and it's stuck on an electrode, and that's what John's going to talk about in his poster, because the molecule's stuck on an electrode and you can shine light on it. You can then very precisely investigate the electron transfer with the electrode. These are some experiments, and one of the things that came out of this is if we cycle the potential very rapidly, we reversibly oxidize and reduce aggregates, just sitting there oxidizing it, taking the charges out. But if you do it more slowly and let the positive charges stay in the particles for a while, it becomes very difficult to remove the charges. Very irreversible. You put the yes.
So, sorry, when you actually make an electrochemical cell out of it, is there any concern that your potential drop or the field is going to be right at the interface and it's going to be perhaps a lot larger than in a real device where the potential drop is...
So first of all, it's a pretty much standard electrochemical device. The only difference is there are a few molecules stuck at the electrode. And now the question I think you're asking, but correct me if I'm wrong, is there any concern that the molecule is bigger than the Helmholtz layer?
Right.
Right. And this molecule is very large, especially if it's an aggregate. It sticks out. Absolutely. So we were very interested to see whether there would be a distribution of oxidation potentials due to that effect. And we got essentially identical oxidation potentials on a pristine particle. And the argument is that all the charges are entering in the part of the particle that's touching the electrode.
I see.
That the potential falls off so rapidly that you can only eject at that contact point. And the way that fits is that we see a bimodal distribution. A certain fraction of the particles don't do anything, and the other ones are nearly identical. And in fact, as it got better and better, that number got narrower and narrower. And what we came to realize is, although this is a dirty interface with tremendous inhomogeneity and oxides as ITO, we began to understand what people have been saying theoretically in the literature, and that is that since it involves charges, there's the distance scale for thinking about this is a electrostatic distance scale. And the electrostatic distance scale was so large that it averaged over the molecular details of the potential, which I think is really very interesting. So a single molecule at an electrode doesn't care about the roughness of what's going on there, as long as it can touch the electrode somewhere. Okay, I'm going to just really, because I'd like to stop and let people ask if there are any more questions. So I'll just tell you what this end part of the paper about, even though it may be the most interesting from an energy transfer. We started doping one polymer with another polymer. Just like John said, connect the donor and acceptor with one covalent bond. Well, that's what he did. more recently, he and others in the group have put one polymer chain in another polymer to be a kind of, not a 0D interface now for energy transfer, but a kind of 1D. And look at that energy transfer, and measure its efficiency and so on, and then oxidize that one chain and look at the effect of that. And it looks like charges can accept energy over surprisingly large distances, even when they're in a different type of material. And we're beginning to have a theory for that. So it could be that there's some good news, for us anyway, and that is knowing all this detail about this problem may ultimately come up with some new insight in how it occurs. And it could be that positive charges in these polymers disturb the polymer in such a way electronically that the quenching radius is surprisingly large. And I'd be happy to answer that. I think I left at least a few minutes for questions. Yes.
Good. So,
I'm going to stop here.
okay.
Yeah.
Questions?
Well, when you show this data on single molecule cycle chemistry, essentially, your oxidation and reduction peak are almost at the same voltage. Or this is just some argument, because they should be separated by,
Oxidation and re-reduction, right.
should be separated by the chromophores, I guess, right?
I see, yeah, great. So what the question was, when we looked at those cyclic voltammetry curves, they had a positive going current and the negative was, yeah. So both of those are the oxidation peak. One is operating from neutral to oxidized and the other is from oxidized back to neutral. The reduction peak would be shifted over. And we have a little bit of an embarrassing situation with the reduction peak. Indium tin oxide strips. For the electrochemistry experiments, we can't do it the reduction peak yet. We've been trying really hard. I do want to point out something. This is really just real basic, but it took us for a while to realize it. When you scan an OLED-like device and you scan the potential from minus 10 volts to plus 10 volts, you move the Fermi potential at the electrode about a tenth of a volt. It's incredible. First of all, you don't move it at all until you start injecting charges. Because, if you're talking about the potential at the electrode, it doesn't change. The potential difference between the electrode and the polymer next to it is determined purely by the Schottky barrier and almost not the field at all, because there's no distance. So in an OLED, when you inject charges efficiently, you're doing it because there's some point further in the device, 10 or 20, 30 nanometers away, which the electric field is operated on the system long enough so the potential is dropped below the ITO Schottky barrier. So when you scan a capacitor, think of it as a capacitor. If you scan a capacitor and you look at that point that's touching one of those plates, its potential is the same as that plate. So how does electrochemistry work? Well, what they add is the electrolyte. And then the potential drops from the potential of the electrode to the potential of the potentiostat within a few angstroms. And that's the purpose of the electrode. It's the dipole that you create that's called the Helmholtz layer, which creates that drop. And without that layer, the potential doesn't drop at all until you penetrate into the device.
So why it's asymmetric? Why it's so difficult to... So you're oxidizing, you're not reducing, right? You are oxidizing, not reducing.
Yes.
So why it's so difficult to reduce?
Oh, well, in the case of the dry device, you swing the potential over such a small value that you can't get it to that number. You'd have to change the Schottky barrier, change the electrode. If you change the electrode, you could do it. Okay. In the electrochemical devices, you can go at anything you want. That's the amazing thing about electrochemistry. You can scan the potential plus or minus 10 volts. But you better not scan it past the point where the electrode then gets reduced to indium metal and so on, because at that point the electrode just leaves the glass and goes into solution. So when we go negative 1 volt, we then strip the indium off. Although we have we've got a new way of doing it using gold electrodes. So we thought that was just great until the gold doesn't. So we were unaware of this. That gold's very complicated material. I thought it would be really straightforward. Gold's very complicated in nanostructured gold. So we'll eventually get it to work. Another question?
You excite molecules with light and molecules so close to the metal. Do you
Yes.
see any evidence of quenching?
Well, absolutely. And that's why we don't use the molecules on metal. We're always using indium tin oxide.
You're conducting, but not really metal.
But even though we're using, indium tin oxide, which is a semiconductor, but it's still, John will be talking about it, but it still has 50% quenching.
You mentioned gold. Gold may be very strong.
Right. So in gold, we put we tried to deal with this and push it off the surface of the gold. Right.
Any other questions? Let's thank the speaker again.